Aloha, everybody. This is Gigi from Kauai Community College. In this video, I want to tell you about how we use calculus in finding volume and surface area of a sphere. And I think that's like one of the coolest thing that I've seen, right? Because I teach geometry, and it was just, a little bit harder to justify the equation on how to find volume and surface area in geometry, but it works out beautifully in calculus. So let's take a look, okay? So suppose you have that sphere that looks like our Earth right there, and we want to know what's the volume. Okay, so how do we find volume? Well, first we need to start with an equation um, of a function, right? And then we're going to revolve it. In this case, the equation of a circle is x squared plus y squared equals r squared. And I'm just going to go ahead and take half of the equation. So y equals square root of r squared minus x squared. And I'm going to rotate that about the x-axis to get the sphere, right? Now, then we are going to, I'm actually going to do the slicing method in finding volume. Okay, so if I take one slice of it, the thickness is delta x, right? And the cross section is a circle. And of course, we know area of a circle is pi r squared, right? R in this case is the y value or the function value. So we have the area would be pi times square root of r squared minus x squared, and then square, right? And notice square will undo that square root in just a second here. And then what are we going to do with a bunch of these slices? We are going to sum them up from 0 to r, right? And that calls for the integral from 0 to r. But if we are going to go from 0 to r, we are only going to get half of the sphere, right? The volume of, say, half of a sphere, like that. Well, we want the whole entire sphere, so we are going to double it, right? So double the integral from 0 to r will get the volume of the whole entire sphere, right? And the area, as we can see, is that. So when we plug it in, we have the integral from, we would say 0 to r pi, and the area comes from there. Dx is the thickness. Okay, and we're going to double that, right? Okay, take the integral. We have 2 pi on the outside because that's the, those are the constants, r squared x minus 1/3 x to the third power. Evaluate from 0 to r. Now, when we plug in the lower limit of 0 into wherever the x's are, we will get 0. So the answer will be left with whatever it is when we plug in the r, right? So when we plug in the r right here, r times r squared is going to be r to the third power, and this right here, r to the third power as well. Nice, because you have like terms, right? So you have 1 whole r to the third minus 1/3 r to the third, you'll get 2/3, right? 1 whole minus a third is 2/3. 2/3 r cubed multiplied by 2 pi. So then we say the volume of the sphere is 4/3 pi r cubed, as you have seen before, right? That's beautiful. That's just beautiful. I think what's even more beautiful than this is the surface area. I have a really hard time justifying surface area of a sphere in geometry classes, but let's just take a look here how we can use calculus to show it easily. Okay, so again, that's the equation, right? Y equals to square root of r squared minus x squared. And then remind ourselves of surface area is the integral from a to b, 2 pi times the function value multiplied by square root of the 1 plus the derivative square, right? Now, we are going to go from 0 to r as our AB. And if we're going to do that, again, we're getting half of the sphere, right? Surface area for half of the sphere. So we want to double that. Okay, so surface area. And in order to do that, we need the derivative, right? So let's go from y equals the square root of r squared minus x squared. So then the derivative is 1 over 2 square root of r squared minus x squared multiplied by the inside derivative. Don't forget that inside derivative, right? And then the 2 divided out with the 2. So you'll have just negative x on the numerator and r squared minus x squared inside the square root on the denominator. And that is what we are going to plug in right here for the derivative. Okay, now, so we have surface area equals 2. We want to double that to get the whole entire sphere, right? 2 pi function value multiplied by square root of 1 plus the derivative square. And if you notice this whole big nasty chunk right here, we have seen that before when we were doing surface area. If we square this, okay, the blue part here, square it, get a common denominator, and clean this whole thing up, it becomes a really nice, beautiful integral. And that is the integral of 4 pi. Where did I get the 4? 2 times 2 is 4, and then the pi there. Then in the integral from 0 to r, and this whole big red chunk right there just end up being r when you simplify that. So you have the integral of 4 from 0 to r of r dx, multiply that to 4 pi. And when you take the integral, the r is a constant because you're taking the integral with respect to x, right? So it would be 4 pi r x, and we are evaluating that from 0 to r. And of course, when you plug in 0, the lower limit to x, you'll get 0. So the answer will just whatever the answer is when you plug in the higher limit, the upper limit r. And so the volume of a sphere is 4 pi r squared. That is really awesome to see, right? And if you can kind of like make sense of this for a little bit, the pi r squared is the area of a circle, right? And better yet, think about the Earth right here. That's the area of that circle right there, okay, in the equator. Now, the surface area of our Earth is 4 times the area of that circle in the middle there. That is so awesome. Like, how does that even work? So that's how you see the calculus working for you, justifying things that you haven't been able to figure out before, right? And that's the beauty of math. So that is it. I hope you do enjoy this extra video in this lesson.